Good evening. My name is Josiah Caprino, and I am joined here with my colleagues Ashwin Varghese, Carlos Miguel, and Harsh Vakaria. What we are going to be discussing today is the memoryless property of the exponential distribution. We will go over its derivation, why it is important, and we will close with some examples of where the memoryless property can and cannot be applied. But first, I will give a brief overview to the exponential distribution. The exponential distribution is a continuous distribution. This means that the exponential random variable can take on any value between 0 and infinity, inclusive of 0. A Poisson process is a stochastic or random process that keeps count of the number of events and the time that those events occur in a given interval. The only parameter for an exponential distribution is lambda, which can be described as the arrival rate. An example of this could be 6 cars per hour or 2 customers per month. Finally, the mean and standard deviation of an exponential distribution are both equal to 1 over lambda.
Now we'll talk about an example of the memoryless property in the exponential distribution. The memoryless property is described in the formula on the first bullet point. It basically says, given you have been waiting a certain amount of time, s, for an arrival, the probability of waiting for more time, t, is equal to the probability of waiting if you had just started waiting. For example, there is a bus stop across your house. When you walk up to the bus stop, John tells you he has been waiting for 10 minutes. Given this information, how much more time do you expect to wait? If the buses follow a Poisson process with exponential distributed into arrival times, the information John told you is useless. The probability of you waiting 10 more minutes would be the same even if John would have been on the bus stop for 2 hours, or any other amount of time. This is the memoryless property of an exponential distribution, and it is one of the basic assumptions in most queuing models.
I will now walk through the derivation of the memoryless property of the exponential distribution. We first see that, by the definition of the exponential distribution, the probability of an event x occurring at a time greater than t is given by the integral from t to infinity lambda e raised to minus lambda x dx, which is equal to e raised to minus lambda t, where lambda is a parameter of the exponential distribution. Now let us assume that event x has not occurred in time s. If we denote y as the event corresponding to the time remaining for the event x to occur, we can define its probability as p of y greater than t given x is greater than s, which, as we see from equation 2, is just p of x greater than s plus t given x greater than s. Then, using the conditional probability formula, we see that equation 2 is just p of x greater than s plus t and x greater than s divided by p of x greater than s. And since the event x occurring at time greater than s is completely included or is a subset of the event that the x occurs at a time greater than s plus t, the term in the equation 3 just reduces to p of x greater than s plus t divided by p of x greater than s. Again, by the formula of the exponential distribution, term 4 is just e raised to minus lambda s plus t divided by e raised to minus lambda s, which is just equal to e raised to minus lambda t. This, as we saw from equation 1, is just the probability that event x will occur at a time greater than t. This implies that the time remaining for the event to occur follows the same distribution as the event, and it does not depend on s, which is the time that has passed.
I will deal with the importance of the memoryless property and some areas where the exponential property assumption can't be applied. The memoryless property of the exponential distribution is very important and has many applications. It means that we don't need to know any information on past events to make a prediction about the future. It greatly simplifies the modeling of queues. Queuing theory involves the study of queues to predict queue length and waiting time, and involves customers entering a system and being served. Customer arrivals in a system are often exponentially distributed, and hence the memoryless property is useful because we don't need to know the prior arrival pattern of the customers. Service times in a system are also often exponentially distributed. Additionally, the memoryless property has applications in reliability engineering. The lifetime of an appliance could be exponentially distributed, and hence its current lifetime will have no impact on how long it will last. The assumption that some systems are exponentially distributed may lead to problems if the memoryless property is applied. For example, if a restaurant has a mean service time of 2 hours and an exponential distribution is assumed, knowing that a family has been there for 2 hours should tell us nothing about how much longer they will be in the restaurant, except that the mean conditional time would be 2 hours. However, this is unlikely. The same problem comes in assuming other systems are exponentially distributed, such as service in a barber shop and wait for a bus at a bus stop. Hence, in conclusion, there are advantages to the memoryless property, but care must be taken on where it is applicable. This concludes our presentation. Thank you.